I'm in Menlo Park, New Jersey. Nice neighborhood. Sort of place where nothing ever happens. But the other side of the street tells a different story. This is the site of Thomas Edison's Menlo Park laboratory, where he made the inventions that made him a household name: the phonograph, the electric lamp. And for our purposes, the most interesting invention was the Edison Effect.
This picture shows an Edison Effect bulb. If you look carefully, you can see a filament, as you'd expect in a light bulb, and also a separate plate. This schematic shows how the Edison Effect bulb works. This filament is heated by applying a voltage across the filament. The plate is shown here. How that circuit behaves depends upon the voltage applied to the plate. With a positive voltage, a current flows. But reverse the polarity of that voltage, and no current flows. Edison received a patent for a device built upon the Edison Effect, but it didn't receive widespread use. But remember that he discovered this effect before the electron was known. The electron was discovered in 1897 by J.J. Thomson, who showed that cathode rays were composed of negatively charged particles and that they had to be a lot smaller than atoms. But the real impetus for improving electron devices came with the invention of radio. Many inventors tried to develop improved detectors that were better than the simple detector that Marconi used. In 1904, John Ambrose Fleming improved upon the Edison Effect tube to build the first vacuum tube diode, and this was widely used to detect radio waves. But Lee DeForest wanted to invent his own detector, and in 1906 he came up with the vacuum tube triode. And this was revolutionary because it allowed not just detection, but amplification. DeForest introduced a third element, this grid. A voltage applied across the grid can be used to modulate the current that flows through the plate. So now by changing the grid voltage, we can change the current that flows across the plate. This first line shows the triode characteristics for a small grid voltage. As you increase the plate voltage, the plate current increases. But as you apply a higher negative grid voltage, that curve moves. Now it takes more plate voltage to give a given plate current. And as we apply an even higher grid voltage, the curve moves farther to the right. The slope of that curve, the slope of the current versus plate voltage curve, is the gain, which is known as GM. That plate circuit also has a very high impedance. And so this combination of the device characteristics and the high input impedance looks remarkably like the MOS transistor. The vacuum tube was revolutionary, but it wasn't perfect. It was fragile, and not so much because of the glass tube, but because of the filaments. They were very delicate, particularly when hot, and vibration could cause them to shatter. Even when they didn't break, they would eventually wear out. Vacuum tubes also consumed a lot of power.
The Edison Effect introduced an entire new class of electron devices that allowed us to not just use electrical energy, but also manipulate signals. But ultimately, vacuum tube devices would prove to be too unreliable. The solution to the reliability problem came several decades later, from a town not far from here, with the invention of the transistor.